The domain of a function is really asking what values can x, our input, be? What values can x be so that we can get an output value? Looking at the symbolic representation of the function, we really want to focus on determining if there are any values of x that we cannot put in for. So are there any values of x that would cause problems with our function, meaning we would not get an output? Taking a look at the first example with polynomial functions, are there any situations where if I multiply, add, subtract, or raise to whole number powers, 1, 2, 3, etc., are there any values of x that would cause my function to be undefined? No, I can do all of these operations with any number. Polynomial functions have a domain of all real numbers. And we can write that in words. We can write it in interval notation with our infinities, negative infinity to positive infinity. Or we can even write it in mathematics. We have a fancy symbol. It's an R, but with an extra bar on the side. And so this is just a symbol for all real numbers, the real number set. There are a lot of functions that fall into this group of polynomial functions, but these are all of those expressions that we were factoring back in chapter 14. When we talk about polynomial functions, we're talking about the exact same expressions that we were working with back in chapter 14, and also linear functions. Linear functions fit into this polynomial function group. So we have linear functions, quadratic functions. We were talking about solving quadratic equations by factoring. It's the same idea here, except now we have function notation. Cubic functions. This just means there's an x to the third in it. So linear functions just have x. Quadratic functions x squared. Cubic functions x to the third. Quartic functions, I think you can see the pattern, quarter, x to the fourth, and so forth. It just keeps going. In all of these polynomial functions, we're just talking about basic operations, multiplying, dividing by numbers, adding and subtracting, and then raising to whole number powers. Moving to rational functions, we just finished our chapter on rational expressions, and now we can talk about those rational expressions in the context of functions. For rational expressions, we had problems when the denominator was 0. So that same situation is going to come up here with functions. I am not allowed to divide by 0. Dividing by 0 is undefined. If I want to talk about what is the domain for a rational function, I need to focus on the denominator. So taking a look at that denominator, we can look at this in two different ways. And I say this because for some of you, one way is going to make sense, and for some of you, the other way is going to make sense. It almost sounds like I'm doing opposite things, but I promise you they are the same. So let's talk about the first way. When we were working in chapter 15, the question was always asked, what values make the expression undefined? So we would take the denominator, set it equal to 0, and solve for the variable. So we're going to solve for x, divide by 2, and x equals 5/2, or we can write it as a decimal 2.5. So 2.5, or 5/2, makes the denominator 0, which makes the expression undefined. For domains, though, we want to know what x can be. What are the values of x that are allowable? Well, in this case, everything except 2.5. So we can write that in words. All real numbers except 5/2, or if you want to write 2.5, you can, whichever form you're happy with. And if we write it in interval notation, I'm going to draw a number line, 5/2 here in the middle. I don't want 5/2, which means I'm going to have parentheses because I don't want to include 5/2. So I'll have negative infinity to 5/2 union 5/2 to infinity. We saw this a little bit with the graphs when we were doing domains and ranges of graphs above with that union symbol. It just means I have two pieces of the number line that I need to take together, and they're just not connected. So this is one way to solve that problem. Find the values that make the denominator undefined, and when you write the domain, you throw them out. Similarly, I'm going to come over here to the side. We can set the denominator not equal to 0, and our domain becomes that. Domain is all x that are not 5/2. And again, why am I telling you both? Because some of you will connect with the first way because that's the way that we talked about it in chapter 15. Some of you may like the other way better because then you don't have to remember that's the value I throw out. Do what's comfortable for you. This domain here, it'll lead to exactly the same interval notation and the same written expression. X is not equal to 5/2. Okay, so for rational functions, we have some context on how to do that because we were doing it in chapter 15. Let's take a look at radical functions now. Radical functions, we're actually going to talk about radical functions in the next chapter, in chapter 17. So we haven't really talked much about it yet, but we can talk about domains for these functions, and we're going to get a little bit of them later on in this chapter, talking about the different families of functions. Radical functions have a root in them, and here we have square roots. And a square root is the inverse operation of the power 2. So x squared and the square root of x. These are inverse operations. They undo each other's operation. For radicals, I cannot take a square root of a negative number. There's not a situation that I have two numbers multiplied together that give me a negative answer. Because when I multiply two positives, I get a positive. When I multiply two negatives, I get a positive. I can't take two numbers that are identical, multiply them together, and expect to get a negative answer. That doesn't work in the real number system. And so we cannot take the square root of a negative number. In order to find the domain for radical functions, we figure out what will make the function not real by setting inside the radical greater than or equal to 0 and solve for x. So inside the radical, that's the x part, greater than or equal to 0. That's our domain. We can write it in words, all real numbers greater than or equal to 0. I'm going to write this one in set builder notation because it pretty much copies what we just wrote over there. X such that x is greater than or equal to 0. We have to let the set builder know what our variable is, which is why the x is in the front, and then curly braces around it. Or we can write this in interval notation. And interval notation, we draw our number line, 0 here. We're doing greater than or equal to 0, so we're going 0 to infinity. So 3 different ways to write our domain here. Let's see if we get more complicated inside the radical. What happens? H of x equals square root of 6 plus 3x. So we take what's inside the radical, 6 plus 3x, and make it greater than or equal to 0. And then we need to solve for x. So I'm going to subtract 6 from both sides. 3x is greater than or equal to negative 6. Divide by 3. X is greater than or equal to negative 2. So our domain, all real numbers, greater than or equal to negative 2. In set builder notation, x is greater than or equal to negative 2. And in interval notation, like I said before, I like to draw the number line and then write the interval notation because that interval notation is shorthand for the number line. So here we go. Negative 2, x is greater than, so it's going to be on the right side. I've got the equal sign there, so I'm going to have equality, which means negative 2 can be in my set. So I would either do a filled in circle or a square bracket like this one. We're going to positive infinity. So our interval notation, negative 2 to infinity. Continue practicing with finding the domain of different types of functions. We know 3 different types of functions. Polynomial functions always have domain of all real numbers. Rational functions, we have to throw out the values that make the denominator equal to 0 because we can never divide by 0. And radical functions, we have to make sure that what's underneath the radical is always 0 or greater. So we take the inside, set it greater than or equal to 0, and solve. Those are the only restrictions that we have on the domain right now as far as the symbolic representations of functions go. We're only going to learn one other restriction, and that won't happen until much later in the semester. So right now, when we're talking about symbolic representations and the domain, we really just need to check, are we dividing by a variable? Then we have a rational function, and we need to find out where that division is going to be 0, where we're going to divide by 0. Or do we have an even root, a square root, a fourth root, a sixth root? Because those are going to create problems when we put in negative numbers. We want to make sure that no negative numbers get under there. And that's it. I know that was a long introduction to functions. So coming up, we're going to talk about linear functions next. Go back to things that you likely learned in your Algebra 1 classes with linear equations.